income of most people. The income of most.
Sorry, Ada, I just noticed that that the whole thing was not recorded, so I just started to record it. Sorry, okay. Sorry to interrupt.
Yeah, no problem. So when you look at so income is a good example, because when you look at income, let's say monthly income, most people will have well, a small or medium income, and some will have a larger income, and then there are a few people or few households that have an incredibly high income. And these will, if you can calculate the mean, always distort the mean. It will also always influence a regression, a linear regression. But obviously, these people do exist, or these households do exist, so we can't just delete them from the data to get a better model or a better fit. So how to deal with outliers and what to do with them is always something that has to be considered. For example, you could also transform the data to, for example, you could, instead of having model the income, you could model the square root of the income, which would decrease the difference between the very large and the normal or smaller incomes. So these are things that can be done. In any case, so outliers do influence linear regression, and they also do influence descriptive statistics like the arithmetic mean, the standard deviation, the variance, and also the regression coefficient. So to compensate, or to, so on the other hand, you also always have methods that are robust, that are not affected like this by outliers. For a descriptive analysis, this would be the median or the EQR, and you also have well, rank correlations, or also regressions that are well, I forgot the name, so that are robust. So this is just to show you that that this coefficient of determination does not indicate whether or not a model is true. Any statistical measure can be misleading. It just gives you a summary. It doesn't, so, and this can be, so how the data really look, so what is behind this statistic or this measure, well, you can only see if you visualize the data. So if possible, you should always visualize. Or, for example, for, let's say, the income, you would, without visualization, because if you have really large data sets or models, or if you repeat too often, you can't really visualize each individual step or data set, then you could at least, you could use robust statistics to get an impression if there might be something seriously influencing a linear regression. So, and this is also true for other measures or coefficients. You should always know the limitations. So what can they show you and what can't they show you? So for a linear regression, there are assumptions that should be well fulfilled. Often they're not, so then we have to deal with it. So the first is linearity of the data. So ideally, there's a linear relationship between X and Y. At the least, there should be no non-linear relationship that can be observed. So for example, a quadratic or logistic relationship, or well, a periodic relationship. So if you see a non-linear pattern or relationship, then you should not use linear regression, but whatever is suitable then. You can easily check, or the best way to check this is a scatter plot, which you saw here for the ANSCOM data. all visualizations are only possible if, well, if you don't have too many models, data sets, variables and features. So this is something that may make it impossible for you to actually visualize everything. There should be no meaningful outliers. An outlier is never clearly defined. It depends on the data. It depends on so it has always, it's always something that is up to interpretation, or mostly. Sometimes it's very clear, but sometimes you have to think about it. You also have to think about, are these outliers errors, which is possible, or do they belong to the data? Then you have to deal with it. These you will also see in the scatter plot. And the other assumptions are related to the residuals, so to the difference between observed value and fitted value. So you should look at the distribution of the residuals. These should be independent, so there should be no correlation between residuals. This is especially true for well, time series or time related data, but then you may use another model anyway. So you can plot the fitted values against the residuals. Then you can see if there's a pattern or correlation. So it should look random. So the pattern should look random. In such a plot of fitted values against residuals, you can also check for constant variance. So there should be along the axis of the residuals, there should be the variance of the residuals should be constant. This is called homoscedasticity. And the residual should also be normally distributed. You can check this with a quantile plot. So often these assumptions are not fulfilled, at least not perfectly. And then the coefficients and the p-values are affected by this. And then there are solutions. So you can then think about what can be done. Is this still acceptable, or do we try, or could we try to transform the data, or well, find some different model or another solution? But there are ways to deal with this. This also holds true for other methods. In case assumptions are not well fulfilled, there are solutions or tips what to do then. If you use a model, a linear model to predict new data, so the predictions should always fall into the range of the observed data. So basically the training data, the training set, so the model, so the data set or the values on which the model is built. So in case of, yeah, let's say the ladder score, there's a certain range. You should not try to predict anything that is way out of this range, because the data is basically, so the model is basically trained or fitted to this range, and you don't know what is to outside this range. Is this a good estimate for values outside this range, data outside this range? So often the variables, the independent variables, are not quantitative but categorical, and you can easily use these also in a linear regression. And then you use something which is called dummy coding. This is done automatically in R and in Python as well, I assume, or you just have to say, please dummy code. So all categorical variables can be dummy coded. It means that so a dummy variable is a variable with values that takes values 1 for yes and 0 for no. Okay, I have to. Okay. So as an example, I give you the country. Basically, the country, or it's a subset of the countries that are registered to the workshops of the Datathon. So we have people from Australia, Bangladesh, Germany, and USA, and other countries. So this is just a simplified example. When we started these workshops, the largest group came from Bangladesh or was from Bangladesh. So this would then be for the reference group, the best reference group. If you don't give a reference group, if you don't specify it, it's set automatically, usually in alphanumerical order. In any case, if we use the largest group as a reference group, then all other groups are given in comparison to this group. So if Bangladesh is true, then Australia obviously is not true, so it's 0. Germany is not true, and US of A is also not true, so it's 0. If Australia is 2, then Australia gets a 1, and the other countries get a 0. And if Germany is 2, Germany gets the 1, and the others gets a 0. So in this way, you can have a dummy coded. You can have a dummy coded variable. If you have k equal 4 categories, as this is the case here, so I gave 4 countries, then you create k minus 1 dummy variables. So these are Australia, Germany, and USA. And this means that, for example, and in the regression model, you get you have then these 3 dummy variables, and for each dummy variable, you get a regression coefficient. For example, beta country USA, meaning country USA yes, and all other countries then no, models the change of y for the case that country equals USA in comparison to the reference country Bangladesh. So how does y change if the country is USA instead of Bangladesh? So that is the meaning of these dummy variables. This works well for, well, a reasonable number of categories. If it's a lot, it's probably, well, then the p-values can be randomly significant. So the groups should also be large enough. So it's a bit, but it's a commonly used. So this is commonly used, and you will definitely need it in case of multiple linear regression. If you have many features, many independent variables, often at least a few of them are categorical variables. So in a multiple linear regression, you don't have just one independent variable, but several. And the regression coefficients better p, so you get one regression coefficient for each independent variable. So you multiply, so you multiply the independent variable with the regression coefficient, and these terms are additive for each independent variable. So you still have a linear relationship. So these coefficients, these estimates, including their p-values, are interpreted all other things being equal, meaning that other independent variables remain constant or unchanged. It's called ceteris paribus. You can, so this is, sorry, I don't know, I have to check the pronunciation again, but it means that, so the terms are additive, so you consider the influence of one independent variable on y, keeping all other independent variables constant, and then you look at the others. So meaning, looking at one independent variable, all other things are kept constant or remain constant and unchanged. You can have many independent variables or many features, and with each independent variable, so with each other influence, each extra variable, each feature, you will probably improve the fit of the model. Probably. then you there's again the problem of the possibility of overfitting. Also, with each extra independent variable, the probability that any of these, the p-values, or that any of the independent variables, so the influence is randomly significant, so that you get a small p-value, but randomly it increases, because you always have, there's something which is called the alpha error, so that you that the p-value is wrongly significant, and this can randomly happen, and the more features you add, the higher the probability that such a case occurs. So then you have to consider that you consider you have a variable that the model shows you is significant, but in actuality, in reality, it's not. So that would be one problem. So in case of multiple linear regression, you have to think about overfitting, and you have to think about the p-values. So if you have a multiple linear regression, the independent variables may depend on each other. So the independent variables may interact with each other, meaning that you can't really consider all other things being equal or constant. This is something that you have to think about. Well, you can check for it as well, but you can also, sometimes you know from the data that it's probable that some independent variables interact, so that they influence each other. And then you can extend the linear model by an interaction term. So there are different ways to do this. It depends on the interaction. So this is then also something that you should consider in case. So you can check for it, but you can also consider it just from understanding the data. So this is basically all I want to say to linear regression. So I already, so Tanzim has quite a few things to say. Do you have questions now? So then maybe we can address them now. Okay, so one other example of regression is, or typical example is logistic regression. It's often used. It's a logistic model, or also called logit model. The dependent variable is binary, so you have true and false. And what the logistic regression does, it predicts the probability of the dependent variable being true. And it does this fitting a logistic curve. I won't go into detail here. There's simply no time, but this is certainly also a widely used method in case you have a binary variable, outcome variable, or dependent variable, then you can use logistic regression. So that's it for today. So these so that's it for the regression part. Yeah, in case you have questions, you're welcome to ask them now. I'm sure you can also ask later, but otherwise I'll hand the lecture over to Tanzim now.
Hi. I think there is a question from Reem. Is dummy coding kind of similar to one-hot encoding? Okay, so Reem, I am going to talk about one-hot encoding. So why don't you find out the answer yourself?
Yeah, I think that's a good idea. Yes. So then, is there another question? So maybe also Tanzim will provide the answer in her part.
Yeah. Okay. So, do we need some break? It's been going on for about